Section 6.4 Impact of Power Height. Since power in the wind is proportional to the cube of the wind speed, the economic impact of even modest increases in wind speed can be significant. One way to get the turbine into higher speed winds is to mount it on a taller tower. Wind speed is greatly affected by the friction that the air experiences as it moves across the Earth's surface. The impact of the roughness of the Earth's surface on the wind speed is expressed using equation 6.15, where v is the wind speed at height h, v0 is the wind speed at height h0, and alpha is the friction coefficient. The friction coefficient alpha is a function of the terrain over which the wind blows. If the terrain characteristic is a smooth, hard ground or calm water, the friction coefficient alpha is equal to 0.10. If the terrain is tall grass on level ground, the friction coefficient is 0.15. If terrain is high crops, hedges, and shrubs, the friction coefficient is about 0.20. Well, the power law given in the equation 6.15 is very often used in the United States. There's another approach that is common in Europe. In Europe, the alternative formulation is v divided by v0 is equal to longitude h divided by z and longitude divided h0 divided by z, where roughness class z, the roughness length z, when the roughness class is water surface, the roughness length z is equal to 0.0002. When the roughness class is open areas with a few windbreaks, the roughness length z is equal to 0.03. If roughness class is a farmland with some windbreaks more than 1 kilometer apart, the roughness length z is equal to 0.1. When the roughness class is urban districts and farmland with many windbreaks, the roughness length is 0.4. If the roughness is dense urban or forest, the roughness length z is equal to 1.6. Figure 6.8a shows the impact of friction coefficient on wind speed, assuming a reference height of 10 meters, which is a commonly used standard elevation for an anemometer. As we can see from this figure, that as the fraction coefficient increase, we can see at the same height, for example, the 50 meter, for the fraction coefficient alpha is equal to 0.1, the wind speed ratio is about 1.18. As the fraction coefficient increases, the wind speed ratio increases as well, which means that even at the same height, the roughness increase, the fraction coefficient increases, the more the wind speed increases. Another way we can see that as the height increase, even with the same fraction coefficient, the wind speed ratio also increases. So which means the higher the tower, the more wind speed we can get. More wind speed also indicate as more power to be generated. So which means as the fraction coefficient increase, the wind power increases. As the height increase, the more more power are generated. Section 6.5, maximum rotor efficiency. When wind approaching from the left is slowed down as a portion of its kinetic energy is extracted by the turbine. The wind leaving the turbine has a lower velocity and its pressure is reduced, causing the air to expand downwind of the machine. So as we can see from the figure 6.9, when the upwind of the machine, the pressure is higher, and after the wind turbine, the pressure is reduced. The speed Vd is smaller than the upwind speed V. Since the pressure is reduced and the air expand, so we can see this, the air that passes through the turbine forms as a stream tube. The upwind velocity of the undisturbed wind is V. The velocity of the wind through the plane of the rotor blade is Vb, and the downwind velocity is Vd. The mass flow rate of air within the stream tube is everywhere the same. Call it M with a dot. The power extracted by the blade Pb is equal to the difference in kinetic energy between the upwind and the downwind air flows. So the Pb is equal to 1/2 mass m dot multiply the v square minus vd square. To help keep this algebra simple, let us define the ratio of downstream to upstream wind speed to be lambda. The lambda is equal to Vd divided by V, which is the downstream wind speed divided by the upstream wind speed. So the Pb therefore is equal to 1/2 rho multiply A multiply V plus lambda V divided by 2 multiply V square minus lambda square V square. Therefore, it also can be expressed as 1/2 rho A V cube multiply 1/2 1 plus lambda multiply 1 minus lambda square. The power extracted from the wind is equal to the upstream power in the wind multiplied by the quantity in the brackets, which is we call the fraction extracted. The quantity in the bracket is therefore the fraction of the wind power that is extracted by the blades. This is the efficiency of the rotor. Usually we design as the Cp. So the rotor efficiency, Cp, is equal to 1/2 multiply 1 plus lambda multiply 1 minus lambda square. Therefore, the PB is equal to 1/2 rho A V cube multiplied CP. To achieve the maximum rotor efficiency, so the CP, we use CP, we calculate the partial derivative of CP to lambda. Therefore, we can obtain as the maximum rotor efficiency equal to 0, set dCP divided by d lambda equal to 0. At this time, the lambda should be equal to 1/3, which means that the downwind speed divided by the upwind speed is equal to 1/3. So the downwind speed will be 1/3 of the upwind speed. And at this time, the maximum rotor efficiency CP will be equal to 1/2 multiply 1 plus 1/3 and multiply 1 minus 1/3 square, and then we can obtain the maximum rotor efficiency will be 59.3%. This means, in theory, the maximum efficiency of a rotor is 59.3%. So the maximum wind turbine efficiency is 59.3, and that is called the Bettis efficiency, or sometimes the Bettis law. So how close the best limit for rotor efficiency of 59.3% are modern wind turbine blades? Under the best operating conditions, the rotor efficiency can approach 80% of that limit, which means the rotor efficiency is about 45 to 50% when converting the power in the wind into the power of a rotating generator shaft. For a given wind speed, rotor efficiency is a function of the rate at which the rotor turns. If the rotor turns too slowly, the efficiency drops off since the blades are letting too much wind pass by unaffected. If the rotor turns too fast, efficiency is reduced as the turbulence caused by the one blade increasingly affects the blade that follows. The usual way to illustrate rotor efficiency is to present it as a function of its tip-speed ratio. The tip-speed ratio is the speed at which the outer tip of the blade is moving divided by the wind speed. So the tip speed ratio is equal to the rotor tip speed divided by the wind speed, which is equal to the RPM multiply pi d divided by the 60 multiply wind speed. The RPM is the rotor speed, revolutions per minute. D is the rotor diameter, the unit is meter, and V is the wind speed. So that completes the section 6.5.